Okay, everybody, so we're going to move on to chapter 2. And chapter 2 is about using integrals to approximate areas and then also to approximate volumes later on. So to begin, we're going to talk about areas between curves. So remember, right, recall that in the beginning of the semester, the first way that we defined integrals as the area under the curve of f of x bounded below by the x-axis. So for an example, right, let's say we had some function, let's call it f of x. Then, right, if this is a and this is b, then the area underneath the curve, right, underneath the curve of f of x between a and b, bounded below by the x-axis, right, that was how we defined the area A to be the integral from a to b of that function f of x. So now we're going to actually see what if we have two curves on one plot. So let f of x and g of x be continuous functions such, let's say, over an interval a comma b such that f of x, all of the values, the y values of f of x are always greater than those of g of x, at least on AB. We want to find the area between the graphs of the functions. So since I don't have much space here, let's go to the next page to look at these graphs. Right, so let's say that this is our function f of x, this is our function g of x, and this is both of them plotted. So you can see that we meet the condition that they're both continuous, right? We don't have to take our pencil off the paper to draw any of these two functions. Remember, that's the definition of continuous. And f of x is also greater than or equal to g of x, right? All of the f of x values are always higher, which means the y value is greater than g of x. So those were the two conditions we wanted to meet. And so basically we want to find, right, what we said was that we want to find the area between the graphs of the functions, right? So remember, like, the area underneath f of x is here in yellow, right? And then the area underneath g of x is here in green, right? But that area, that green area now gets removed, right? Because we only want the area in between the graphs. So how do we define this? Right, so let's call this area R. So the pink areas is what we want. So we're going to let R denote, which just means that's going to be the region bounded above by the graph or the curve of f of x, below by the graph, right, or the curve of g of x, and on the left and right by x equals a and x equals b, respectively. So as we saw on the graphs, right, the area in between of R is given by, right, so we need to do the integral from a to b, right, because it's still bounded on the left and right by a and b, of f of x, right, so we had this whole area, and then we took out this area, so we had right? Remember, if we have subtraction of two functions, we can do it together as an integral, one integral, or separately, right? So these are equivalent. Okay, so what we did is we took the area under F, and then we took away the area under G, and that left us with the area we were interested in finding. So that's how we define the areas between curves. So let's do an example. So if R is the region bounded above by the graph of the function f of x equaling x plus 4 and below by the graph of g of x equaling 3 minus x over 2 over 1 to 4. Find the area of the region R. So remember, we denoted, right, we defined R earlier, right, to be the integral from a to b of f of x minus g of x, right, where f of x is always greater than or equal to g of x. So they tell us in this example that the region is bounded above by this f of x, right, and below by this g of x. So we don't really even need to graph this function to know how to set this up, right? So for us, we're going from 1 to 4, and then the above function we know is x plus 4, and then we're going to take away the bottom function and make sure you put it in parentheses so you don't mess up the signs, right? Because you're subtracting the entire function. You're not just subtracting 3 and then the rest. Okay, so that's how we set it up. So let's simplify inside of the integral first. So we need to make sure we distribute this negative sign to both terms. So this becomes x plus 4 minus 3 plus x over 2, right? Because a negative times a negative is a positive. So then this becomes the integral from 1 to 4 of 3/2 x, right? Because 1/2 x plus x, that's 3/2 x. And then 4 minus 3 is a positive 1. Right, and now we're able to do the antiderivative term by term, right? So we do, remember, we can just keep the 3/2 and then we add 1 to the exponent and divide by the new exponent. And then 1, that becomes 1x, so I'm going to just write x. And then that is at 1 and at 4. So this is 3/4 x squared plus x at 1 and at 4. So that becomes 3/4 4 squared plus 4, right? Me plugging in the top bound, so both terms, and then subtracting, let me plug in the bottom bound, which is 1. So that's going to be 3/4, and 1 squared is 1, so I'm not even going to write that, plus 1. Again, you need to make sure you put it in parentheses so you distribute the negative sign to both terms, or you're going to get the wrong answer. So this becomes 3/4 times 16 plus 4 minus 3/4 plus 1. So 3 times 16, that's what? 48 over 4. And then we have plus 5 minus 3/4. So this is going to become, right, 48 divided by 4. That's actually just 12. And then, I made a mistake because I said that I was going to distribute this negative sign, but I kept it as a positive sign when I wrote it. Silly old me. So let's get rid of that. So that's a minus 1. So it's actually 4 minus 1. So this is actually a 3. So we have 12 plus 3 minus 3/4, right? So we have 15 minus 3/4, and that's just going to be 14 and 1/4, equivalently 57 over 4. However you prefer the answer. or how you're asked to give the answer, I should say. And that's the answer to what's the area of R. So R is this area. Thank you.